ECM tooling. Tooling design is the key to successful applications of ECM. There are two aspects of the design of ECM tooling. The first is the determination of the tool size together with appropriate machining conditions necessary to produce the required shape. It should be borne in mind that it is still necessary to make considerable modifications in the machining conditions by the trial and error method. The second part of the tool design is concerned with making the tool of appropriate material, focusing it on the machine, connecting it to power supply, arranging an adequate supply of electrolyte between the tool and workpiece, and insulating a part of tool to prevent overcutting and generating a taper. ECM tooling techniques and examples. Figure 1 shows a simple round tool. The leading edge is sharp and the shank is not insulated. This type of tool produces a hole with considerable amount of taper because the complete surface area of the hole produced is being constantly machined. Figure 2 shows the same tool with insulation on the sides. This limits ECM action extending from the tip of the tool and the top of the hole, and no significant taper is produced. This type of tool is still quite apt to produce striations because of the electrolyte tends to become turbulent as it passes around the sharp corners. This will have an adverse effect on the ability to hold tolerances and surface finish, as well as to encourage arcing and possible shorting at the corners of the tool. Figure 3 shows a tool with its leading edge raised to encourage uniform electrolyte flow around the corner. Also, a tip braced on the shank of the tool allows easy replacement and use of materials such as tungsten and copper to prevent damage in the event of arcing. Figure 4 shows yet another improvement that has proved effective in eliminating any significant taper encountered in the previous methods. The overlap of the tip causes the electrolyte flow to break up as its effect of any stray currents which are likely to cause additional machining over the already finished surfaces. Figure 5. In all the adopted methods mentioned above, the flow of the electrolyte is from the inside of the tool cut around the cutting edges and up through the hole. Figure shows a tool which has its tip flush with the main body and insulation. The electrolyte flow is reversed. This technique produces holes with minimum taper and excellent finish.